Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. So today I am going to discuss on the review of chapter 4, which is threads. Okay, so let's start. So let's focus on what you need to know on this chapter. So there are following outcomes. So you can see from here what you need. The first one is what is the thread? What is thread? Second one is the difference between user level thread versus kernel level thread, and then you will know how to use which one in which applications. Okay. Then we have a parallel application that follows the MDS law. From here, then we can predict what is the speed up. Okay, so we can predict the speed up of a parallel program. And the last one will be thread experiment using RAS. Okay, so let's move on. So the first outcome is what is a thread. So as you can see from here, this is the difference between the process and the thread. Okay, as you know that the process has the process control blocks, user address space in which you have the memory, the program. So it has program and data. You have user stack and kernel stack. User stack is used for calling user functions, and kernel stack will be used for calling kernel functions. Okay, what are the kernel functions? Let's see later in a moment. Okay, so as you can see from here, the thread is part of a process. Okay, you can see from here, thread is part of a process. It has its own thread control blocks. Okay, it has its own user stack, kernel stack, and interestingly, it has the same user address space, the same memory space with the process. So what does it mean? It means that the kernel number one can read the memory here, and also can be read also by kernel number two, and can be read also by kernel number three. So this is called this is used normally for the shared memory programming model. Okay, this is shared memory programming models. Okay, what we have here also, what you can see, why do we have thread? Because now we are beginning on 2000 and above. The CPU manufacturers now use the multi-core or multi-processors. So instead of one core, now they have two core, for example, C1 and C2. Okay, C1 and C2. Okay, so you have here, you can see here, it read the same memory. Okay, from here also you can see that previously what you'll have, if you have two programs, if you have uniprocessors, okay, then we only can do interleaving. Okay, so process 1 and process 2. Okay, so you can only do like this. Okay, but when you have multi-processors or multi-core, okay, you can use also overlapping. Okay, so this is the overlapping. Okay, so interleaving and overlapping. Okay, so this is the difference. Okay, so whenever you have multi cores, and then you can have two process or two threads running at the same time. So if you have process one, for example, this is process one with three threads, okay, and you have dual core, then you can rearrange based on the thread. So T1, T2, and then the T3 can be run after it finished, for example, like this. This is T3, T1, T2, T3. Okay, you can run something like this. So you can do overlapping. Okay, is it clear? So what are the usage of thread? So thread can be used for many things. For example, like this one. While I'm doing the PowerPoint, at the background also there are screen recording. Okay, so minimum two threads here. Okay. So now let's see why we use why we use threads, because thread takes less time to create a new thread than a process. Why? Because it's belong in the process. Okay, and then from the process then it can create threads. Okay, the second one, less time to terminate. So we have create, terminate, less time to create, terminate. So if you allocate the process, then you need to, if you see here, this is the memory, then you need to allocate here P1 and so on, P2, process number one, process number two. But if you are creating the thread, so the thread is belong to the process. Okay, so if you use P1, then you can create T1 here, T2 here, and so on. Okay. And then switching between two threads takes less time than switching between process. What is switching? This is switching. Okay, so this one is switching. Okay, switching between P1 and P2. So switching between two threads takes less time than switching between process, because you don't need to remember what we need to do when we do process switching. We need to save all the states and so on. We need to load the previous process control blocks and other things. There are many things to do. Okay, but if you are on the belongs to the same thread, same process, sorry, then it will be less time to switch. Okay. The next one, threads will enhance efficiency in communication between programs. Why is that? Because now if your one is blocked, for example, you have here, for example, you have process 1 and process 2. Okay, you have T1 and T2 here, and also process 2 have also T1 and T2. Okay, so T1 can do I/O communications. Okay, can do I/O communication, and then while it is blocked, then T2 also can run at the same time. So you can see it will be more efficient. Okay, so that's the first learning outcome. The second learning outcome is about the ULT versus KLT. So when you need to use ULT, when do you need to use KLT? Okay, as you can see from here, this is the this is user space, this is the kernel space. Okay, so we have two modes here, minimum two modes. So in Linux or in Windows, you have admin mode. Admin mode will be in here, or kernel mode, and user mode, which has less privilege. Okay, so if you want to access some function call, okay, like this system call, okay, or for example process control, switching between process, or file management, open, delete, copy, and so on, device management, information maintenance, like how long it takes, the date, the time, and so on, and communications also, then you need to call the system call. So whenever you want to do system call, then you need to go into the kernel space. Okay, so you need to switch into the kernel mode. Okay, so remember the mode switching. Okay, so we need to switch from user mode to kernel mode. So normally the roots or the admin or kernel mode use 0 and the other use 1. Okay, so let's see what are the benefits of KLT. So as it is on the kernel mode, the scheduling can be done on the multiple processors. Okay, so because what you call this on the kernel, then it can switch, means that the one that we put earlier, like T1 here and then T2 at the same time, it can be done. Okay, it can be done in the KLT. Okay, if it is ULT, then you need to have per process here. Okay, you need to have per process. Okay, the other thing is one thread if block is blocked and other thread can run. Okay, so this is for the communication efficiency earlier, and then the thread itself can be multi-threaded. Okay. Okay, well, what about the ULT? So in the ULT, so what you have here is thread switching does not require kernel mode privilege. Okay, you just need in the user mode. The scheduling can be application specific, so means that the user can decide its own whether you want to use round robin, for example, every 1 second switch, or you want to use first come first serve. So it can be application specific, but in KLT it will be decided by the OS. Okay, and then ULT can run on any OS. Just use the same library. Okay, library. Okay, so for example, you have the library called pthread. This one can be in Linux, in Windows, and in Mac OS. Okay, so you can run multiple in multiple OS. Okay, so this is the difference between ULT and KLT. And also, if you read the PowerPoint, okay, you can see that the switching in KLT is take longer, around 10 times. Okay, so you switch between thread in the KLT, it will take around 10 times than ULT. So ULT is faster. Okay, ULT is faster, but if you have so many system call, then the benefit will be offset. Okay, so depends. Okay, whether you want to use ULT or KLT, depend whether you have some heavy IO, for example, you have so many communication, then it will be faster if you're using the KLT directly. Okay. Okay, so let's move the next one. The next one is about the MDS laws. Okay, so the MDS law stated that the speed up. So if you have using, for example, two process, then the speed up is 1 over alpha plus 1 minus alpha over n. So alpha is the sequentials. Okay, in percentage, for example, 0.2, 0.3, and 1 minus alpha is what you call the parallel part. Okay, 1 minus alpha is the parallel part. Okay, you can also measure this one using the time. Okay, so this is time used for using one core, and this is time used using the n core or p core. Okay, so using n core or p core. Okay, so let's see the example. So for example, you have one sequential programs. You have one core here, and it takes, for example, 100 seconds to make it easy. Okay, 100 seconds. Okay. Then it was found that the sequential part is 20. Okay, so the alpha will be 20 over 100. It is 0.2. Okay, so this 20 means it cannot be divided. Okay, cannot be divided. So what is left here is the 80. So 20, and what is left here is 80. Okay, the 80 can be divided if you have two cores. Okay, if you have two cores, then the 80 can be divided into 40 and 40, but you remember that you can run in parallel. Okay, you can run in parallel. Okay, so this is the sequential part, you can divide it, but the rest, the 80 second, then you can run in parallel, so it will be 40. Altogether, you can see 20 plus 40, this is the parallel time, is 60. Okay, the parallel time is 60. So what we have here, so the speed up is T1 over TP. So or n here, so this is T parallel. Okay, I mean T parallel. So 100, this is the T1. Okay, and this is 60. So you can see this is measure 20 plus 40 is 60. So this is 1.667. Okay, can you follow? So now you can see here, although we have two cores, but the speed up is only 1.667. Okay, so you unless if you have this is zeros, then it can be divided 50-50. Okay, so it will be 100 over 50, it will be exactly 2. Okay, now let's see what if we now implement into the 4 cores. Okay, if we are using the 4 cores, then what will happen? Only the 80 now can be divided into 4. Okay, so you have 20, 20, 20, 20, altogether 80. So then the time parallel here is 40. So what will be the speed up? So the speed up with T1 over TP, 100 over 40 is 2.5. So you can see here, 4 cores, the speed up is 2.5. Okay, can you follow? Yeah, so now let's calculate using the MDS law. Okay, so you can see from here, this is from this laws. It will produce the same thing. Okay, using the, so this is called experimental speed up. Okay, this is experimental speed up, and this is using the formula. Okay, so what you see from here, 0% is alpha is 0.2. How do you get 0.2? The red one here. Okay, the red one can be divided, so 20 over 100 is 0.2. Then you substitute. If n is equal to 2, mean 2 cores. Okay, speed up is equal to 1 over 0.2 plus 1 minus 0.2 is 0.8 divided by 2. So 0.2 plus 0.4, 0.6. So you have the same thing, 1.67. Similarly, you can calculate with n equal to 4. Then it will be 2.5. Okay, it will be 2.5. Okay, so it will be the same. So what we can see from here, okay, before I move on to this one, what we can see from here is now also if alpha is 0.2, also you can predict, okay, as infinite, what is the maximum speed up that you can achieve. So you just put here limit n equal to infinite, 1 over alpha plus 1 minus alpha over n equal, so this one will be 0 because divided by infinite, so it will be 1 over alpha. So this is 1 over 0.2. So this is equal to 5. What does it mean? It means that, for example here, although my computers here, AMD Ryzen 7 8 core, but the logical processor is 16, has 16 cores, okay, but the maximum speed up is only 5. Okay, the maximum speed up is only 5. So this is how do you look if you are using Windows, and this is how do you look if you are using the what you call, if you are using the Linux. Okay, you try stop here, and this one using the task manager. Okay, so what you can see from here, then what you call, this is the Amdahl law, so you can predict the speed up. Okay, so I hope you understand the learning outcome number 3. The last learning outcome is about the RAS. Okay, so why is RAS? Okay, so because of the keyword here, this is modern system programming language, modern system programming language 2009, and then focus on the safety, speed, and concurrencies. Okay, so that's why we use the RAS. Okay, because of these uh, three features that we can have. Okay, but of course that because what you call, the one of the drawback is the learning curve is steep, something like this. Okay, so this over time, and this is the learning curve. So you'll find that it'll be difficult at the earlier stage. Okay, so you need to understand the syntax, you need to understand the behavior, and so on. Okay, and it's just like looks like you are fighting with the Rust compiler. Okay, at the early stage here, but along the way, then you can produce the system that is safe and fast. Okay, and also you have a great concurrencies. Okay, and also the many big company has now using RAS. Okay, for example, Microsoft, about 70% of the security is because of the memory problems. Okay, and then RAS take care of that memory problems. Okay. Okay, so now the question is, how can we parallelize our sequential program? Okay, how can we, for example, like this. Okay, if you remember the first one, okay, then this one, of course, you cannot do anything, but if you have the rest, then it can be make it parallelized. Okay, how do you make parallelized? The easiest one is from the for loop. Okay, you can make it parallelized from the for loop. Okay, why is that? Okay, so for example, you have the looping for I equal to 1 to 100, for examples. Then you have, for example, two cores. Okay, two cores. Then core number 1 can handle 1 to 50. Okay, core number 2 can handle 51 to 100. Okay, so it will be faster. Okay, can you see? Yeah, of course that in the for loop, you don't have dependency from the previous result. Okay, independently parallel. Okay, independently you can calculate some of the computation without needing the previous one. Okay, so then you can split. Okay, otherwise you cannot split. If you have four cores, the same thing. Okay, four cores. So now you can divide into four cores: C1, C2, C3, C4, and so on. Okay, now you can the split 1 to 25 here, 26 to 50. Okay, 51 to 75, and 76 to 100. Okay, so you can see from here, and Rust have at least three methods at least, but you can have more using the native thread. Okay, so by design, you have the self concurrencies. Okay, the concurrency will be discussed on the chapter 5. Okay, in more details. Okay, but one of the problems is data race. Okay, the data race. Okay, means the loser will take all. Or you can use the crossbeam crate. Crate is like the library. Okay, you and then uh, the one that we use is Ryan crate. Okay, so this is the cargo is the compilers. I mean the project builder. Okay, so this is also one part of the modern tools. You can see from here. Just see the Rust exercise on parallelisms. Okay, just try the code here. Okay, and the last one here, number 8, making single code parallel using Ryan. So you will see how it works. Okay, how to use the cargo, how to create a new project, and then the cargo will download automatically your dependency and so on. Okay, so it will be easier. Okay, of course the rest of you need to have a steep learning curve. Be patient and just keep trying. Okay. Okay, so I hope it's what you call, you can try the RAS. Okay, you can try the RAS because this is part of our learning outcome to use the modern tools. Okay, so that's it for the chapter 4. If you need any help, please let me know. We can communicate using the telegrams, using the ECIE4314 mailing list, and also link. Okay, so I'll see you soon, inshallah. Okay, so